Over there. Over there. It's got to come up soon. It's not a star. It's not a plane. That's the International Space Station. Of course, I've seen that many times before, but it's always nice to see the space station with your own eyes. Okay, status check of your system, please. We're heading for a maneuver with an execution time of 0837. I'll be asking you subsystem status checks shortly.
Audi, go ahead.
Affirmative.
Now the stations, please.
I think the activities are light.
Parameters on board until we...
Flight dynamics, OD.
Analyst Stuart.
How long will it take you to recalculate?
1343.
Copy that. And the external power supplies?
So, ready for operation?
Copy, thank you. Okay, thank you, sir. Our satellite was suddenly gone. No signal. Condition red. We had to re-establish contact quickly. Now all we have to do is find the problem. Of course, that wasn't real, but just a simulation. We're rehearsing for the worst-case scenario. Our satellite doesn't even notice. Strictly speaking, we're here for cases like this. But we prepare well. When we launch a satellite into orbit, we make sure that it follows a path that we have precisely calculated. We have a group of 80 people to do that, our flight dynamics team. They know all about the attractive forces of the Earth, the Moon, and the Sun, and they calculate the exact launch time and the precise orbit for the satellite, whether it is to orbit the Earth or to fly to other planets. Just for comparison, the International Space Station, which we saw earlier, flies between 300 and 400 kilometers high. That would put it about there, on the first floor above us, so to speak. Our little friend Cryosat from the simulation flies almost twice as high at about 700 kilometers, which would put it about there, in the second floor. Every mission begins with the launch. For us, this is usually at the European spaceport in South America, in French Guiana. And we're there as well. We have direct radio contact with the satellite in the belly of the rocket, and we have tracking facilities like these in the Azores, with which we receive the flight data of the rocket and observe its ascent. This is particularly important when the satellite finally detaches from the rocket and we assume full control. From this moment on, we control the satellites throughout their entire lifetime. That might be 1 year, or 10, or even more. Long-term missions are a key advantage for monitoring the Earth and to understand its physics. Our new fleet of Sentinel satellites is growing. They fly in low orbits and provide accurate data about our changing environment and help answer questions like, why do the oceans warm up? Why does farmland drain? And why does the atmosphere pollute? Or why does the Arctic ice melt? Such environmental satellites have revolutionized science. The detection of the ozone hole and global warming, rising sea levels, thousands of new findings thanks to our environmental satellites. Here you can see how many satellites we've already controlled. Not only our own ESA satellites. Sometimes we carry out the first critical phase after launch for others. Because rockets don't put satellites straight into perfect orbits. They give them a shove, and we have to ensure with a series of maneuvers that they go from the egg-shaped elliptical orbit to a circular orbit. We're experts at this. Like we did for Galileo, this network of 30 advanced navigation satellites has its own flaw. In about 23,000 kilometers altitude. That will put it up there. Now, since Galileo has started work, ESA provides its expertise to the system operators. We calculate the most accurate orbits and improve the flight precision of the satellites. We help solving problems and have already begun developing the next generation of Galileo. In Europe, we're part of a large network. We also do this for weather satellites and telecommunication satellites. They are in a geostationary orbit, always at the same point above us. This orbit is in the 4th floor, at exactly 35,786 kilometers. This is carefully chosen, so that the satellites need exactly 24 hours for an Earth orbit. And because the Earth rotates at the same speed, these satellites remain stationary over us, and TV dishes do not need to be constantly readjusted. This 4th floor is very popular. More than 500 satellites are orbiting up there. Not all of our satellites are in round orbits around the Earth. Some are in highly elliptical ones, sometimes very close to the Earth, sometimes a very long way away. Some satellites orbit the Sun in the Earth's shadow. This is an ideal dark area to look deep into space. Our space telescopes produce images of distant galaxies, the birth of new stars or giant stellar explosions. Not only do we control these satellites, we also transmit the images to the scientists, round the clock, 24 hours a day, because you never know what might happen. Our engineers are masters at solving problems. When our Mars Express satellite was unable to unfold its radar antenna, they kept at it and put the satellite into a spin, until finally the antenna snapped out and locked into position. Since then, it has measured the whole of Mars and delivered accurate 3D maps for our future robotic missions, just like our second orbiter, TGO, which is our new science lab and a permanent relay station around the Red Planet. Now we're ready to fly the first European planetary rover to Mars in 2020. Both the orbiter and the rover search for traces of life on Mars. Just imagine if we find something. That would change our entire perception of life in the universe. Sometimes our colleagues introduce faults, like in the simulation. We sit here in the main control room and wait for them to program a fault into the system. Suddenly, it starts beeping, and we have to find the problem they've set for us. Otherwise, this MCR is only used for difficult and complicated operations. During long-term operation, every mission has its own dedicated control room, and also very specific ground stations that we run by remote control from here. We're spread across the whole world and still work closely together. We manage our environmental satellites from Kiruna in northern Sweden. They fly over here 15 times a day and download in a few minutes all the data they've gathered. We control some satellites from Belgium. There's a great facility in the Ardennes that we use for a wide variety of missions. For other satellites, we use our deep space network of 3 giant dishes in Spain, Argentina, and Australia. We have the most advanced network around the world. These 35-meter dishes are technical masterpieces. 500 tons of steel, but accurate to just a minute of angle. We use them for missions that fly far into deep space. For example, for Rosetta, our comet hunter. After a 10 years journey through space, Rosetta locked onto the comet and followed its journey for almost 2 years. The Rosetta mission delivered the first solid proof that the building blocks of life originated from comets. And it has sent us thousands of high-resolution images about the comet's coal-black, abstract landscapes. Never before has such a small body in space been orbited, and our flight dynamics and operations teams broke new ground almost every day, as well as in 2014. When Rosetta's small lander Philae touched the comet's surface and started beeping, we could hardly believe it all worked so smoothly. And at 400 million kilometers distance, that was unique. Global cooperation is very important in space. We work very closely with Russia, the US, and Japan, and so our reputation grows in scientific and planetary missions, on the International Space Station, and in our work to maintain a clean space environment for future generations. Today, ESA in Darmstadt is one of the world's leading centres for the monitoring of space debris and the issuing of regular warnings, as not only satellites and the ISS are flying around in space, but also countless bits of debris, rocket remnants, old satellites, and even the odd astronaut glove. We can tell you exactly what bits are moving where. We know about practically everything that's larger than a fist. But not only that, we monitor space weather. For example, the violent plasma eruptions from the sun that can severely harm our satellites. And we track about 15,000 near-Earth objects, chunks of ice and rock in our solar system, and calculate the risk of an impact on Earth, because we want to be prepared in case one of them turns into a real threat. We leave nothing to chance. We have nearly everything under control. After all, we are a control centre.